This is a remote for
Yes.
moving slides and
Just left and right.
here and there.
Yep. It won't work until
Until
talk
you-
starts, but yeah.
Yeah.
Welcome to day 2 of the conference. And Marion Sheepers will get us started with Rothberger boundedness and topological groups.
First of all, I want to thank the organizers for the privilege of being here at Gary's conference. And I never had the courage of being mentored by Gary, like Stephen and Dan and others in the room. But I've read his papers, his inspired papers, and I think that was the mentoring that I needed. Happy 70th, Gary.
Thank you.
All right, so Rothberger boundedness in topological groups. My slides are not perfect. One of the things I haven't figured out yet is how to have things show when I want them to show and not show when I don't want them to show. So bear with me about that. So there will be 3 parts to the talk. I'll first talk a little bit about background and then GBC and instances. It's not something from the periodic table.
Could you stand on this end?
Yes, sure. It's not something from the periodic table, and then something about the status of GBC, even though there are openings, I see. But okay. So we're going to start with the selection principle. I know it's a big surprise. So the symbol S1AB means if you give me a sequence of objects from the family A, I can pick a member from each of those so that the selected set of things is from the family B. And those of you who have worked with moving all families and so forth, have encountered this. Script A would be, for example, the collection of moving all families, and script B would be the collection of families with discrete open expansions. But that's not going to be the topic of the day. We're interested in the following. So we start with a subset X of a topological space Y, and one of the things that's going to show up quite a bit is this O subscript X, which is the collection of covers of X, the subspace, by sets that are open in Y, the big space. And now that I've used X and Y, I'm going to immediately switch to something else. We're going to look at topological groups, and for a fixed neighborhood of the identity, we're going to look at all the translates of that neighborhood, and that, of course, is going to create an open cover of the topological group. And this type of cover of a topological group, this collection of covers, I'll just denote by O subscript NBD, the neighborhood open covers. So this is the collection of all the covers that can be created by taking a neighborhood and translating it. One fixed neighborhood and translate it. And so our selection principle that we're going to look at is, you give me a sequence of these types of covers of my group, and we have some subset of the group also. And the question is whether or not I can pick one from each of those neighborhood covers so that what's been chosen would actually cover the subset, the given subset of the group. And subsets that have this property that you can actually find covers of them this way will be called Rothberger bounded subsets of that topological group. The notion Rothberger bounded has been around maybe for about 15 years or so, but it's really a descendant of a much older concept. Breldman defined the notion of strong measure zero, not using that terminology, way back in a paper that appeared in 1990. And the definition was, give me a sequence epsilon n of positive reals. Think of those as neighborhoods of 0. And then one can find the corresponding sequence of translates of those neighborhoods of 0 that would cover the subset. And if a subset of the reals has this property, it's called strong measure 0. And so in our case, we take the group of reals with addition, and the Rothberger boundedness really just translates to strong measure 0. All right, so it's a familiar concept. It showed up a long time ago, and we're just looking at some shall we say, generalizations. Now all the topological groups that we'll be talking about are going to be assumed to be T0, and by I think it's an old theorem of Kakutani or somebody. That means they're already T3.5, but they don't have to be T4 and so forth. So I'm not going to keep on saying T0 topological group or something, I'm just going to say topological group. Alright, and then Borel, of course, made the famous conjecture in 1919 that strong measure zero sets of reals must be countable. And I'm going to use BC to denote Borel's conjecture. And the status, of course, I think these things are well known. 1928, Sierpinski showed that CH implies the negation. If you take a loosened set of reals, it would have strong measure zero, but it's uncountable. And then when Gödel proved the consistency of CH relative to consistency of ZFC, of course, that meant negation of Borel's conjecture is consistent. And then in 1976, Richard Leiber gave the consistency of also the Borel conjecture. So this is a statement, simple statement about sets of reals that's actually independent of the axioms. All right, now there are several equivalent forms of Borel's conjecture, and we're going to pick on one of those. The other, well, okay, maybe I should just say. So, this red statement here, each Rothberger bounded subset of a second countable topological, second countable topological group is countable. So second countable topological groups mean metrizable. Berkhoff and Kakutani, I think maybe. But anyway, so there are other equivalences. One can be stated in terms of the determinacy of some game. There's a game that's associated with this strong measure zero property. And Galvin proved a long time ago that if player one doesn't have a winning strategy, the set of reals must be strong measure zero. And if two has a winning strategy, the set of reals must be countable. So if you assume the determinacy of this game, you get exactly Borel's conjecture. And also there's this nice description of strong measure zero in terms of translates of first category sets. I'm not going to go into that, but one can also state number 3 and a number 4, and there are several other equivalences. We're going to pick on the red one for now. All right, and now we get to this GBC. So we're going to look at more general topological groups, but not dramatically more general in a certain sense. Topological groups are zero bounded if every cover of this kind, where you take a neighborhood and translate it around, if every such cover has a countable subset of cover. So it's a sort of Lindelof property, but it's a lot weaker than Lindelof. And these groups have been, or this notion has been introduced by Guran in the 1980s. And he has this interesting theorem that the topological groups are zero bounded, if and only if it's as a topological group, it embeds us into a product of second countable topological, so into a product of separable metrizable groups. And when one looks at some of these other zero bounded groups, it's kind of surprising. I'll quickly just go through a few quick examples. Very familiar ones, 2 to the kappa. Under usual addition, any kappa, that would be an out of zero bounded group. Of course, the reals to the kappa. Every Lindelof group would be of this kind. Every sigma compact group would be of this kind. Here's the old theorem of Corson. You take this family of sigma compact groups, and you take the subgroup consisting of elements with finite support. That's a sigma compact subgroup. And if the GIs, for example, are all countable, then you would actually get that the entire group is Rothberger bounded. So this means that you can make Rothberger bounded groups of arbitrary large cardinality. Comfort looked at something similar, but put the G delta topology on, and this finite support subgroup actually turns out to be a Lindelof P group. And to me, it's sort of counterintuitive that this should embed into a product just a Tikhonov product of a bunch of separable metrizable groups. Anyway, so these groups G that show up here are also Rothberger bounded groups, and they're also of cardinality kappa. So you can make big Rothberger bounded groups. All right, so here's GBC. GBC stands for global Borel conjecture. And we're picking on that red statement of earlier. So each Rothberger bounded subset of an L of 0 bounded group G has cardinality at most the weight of the group. Right, so we were looking at groups of countable weight when we were looking at the Borel conjecture, and now we're just looking at L of 0 bounded groups and subsets of those, and declare that the only Rothberger bounded subsets will have cardinality at most the weight of this group. And one can of course look at specific instances where you fix a kappa and you look at groups of weight kappa. And so BC sub kappa would be the statement for kappa, that every Rothberger bounded subset of an L0 bounded group of weight kappa has cardinality at most kappa. So these are this is sort of the full generalization that we would want to look at. And these would be instances. So since we don't understand yet the full generalization status, one, I guess, normally starts with instances of it. And of course we already know BCL of 0, the usual Borel conjecture is independent. It turns out that this GBC, you can make it fail totally, very easily, the same way that you make the Borel conjecture fail I mean not with negation, not with CH. But if you add LF1 Cohen sets, Cohen reals, then every Rothberger bounded, every L of 0 bounded group from the ground model turns out to be Rothberger bounded in the extension. And so 2 to the kappa, for example, from the ground model would now be Rothberger bounded in the extension and to have size 2 to the kappa and weight kappa. And, so yeah, and this happens at all the kappas once you've added LF1 Cohen reals. So it's a very simple thing to kill it everywhere. And so I guess on the one hand this tells us that we shouldn't expect to be able to assume some large cardinal hypothesis and then automatically from that derive some specific instance maybe of this Borel conjecture. So what can we actually achieve then? It turns out that if you assume the consistency of a one inaccessible, that means an inaccessible with kappa many inaccessibles below it, then you can build a model in which you have Borel's conjecture and Borel's conjecture at L of 1. So every L of 0 bounded group of weight L of 1 has the property at all Rothberger bounded subsets of it has size at most L of 1. The one inaccessible, so one has to build a model in which you have Borel's conjecture. This is this iterated forcing thing, and in the process you also want to make sure that you maintain BC L of 1, or at least build it in. And this has something to do with Kurepa's hypothesis and killing it and keeping it dead and making sure that sets of reals that are strong measure 0 eventually are just all countable. And that's why we needed all these inaccessible cardinals to get all the way.
Is L of 2 equal to the one inaccessible cardinal?
Yes. Yes. So another observation is that 2 to the L of 1 equals L of 2 does not have the effect on BC L of 1 that 2 to the L of 0 equals L of 1 had on just BC L of 0. And all right, so we could also look at L of n's for n's bigger than 1. It turns out we need a little bit less to do this work. We could get Borel conjecture plus BC L of n at this n bigger than 1, and it fails at all the other L of k's. In fact, it fails at all regular uncountable kappas, and it fails at all kappas of countable cofinality. And we have this version of CH. I don't know, not looked at it hard enough yet, what happens at singular strong limit cardinals of uncountable cofinality. I suspect something different might happen there, but I don't know. All right, and here we actually have an equiconsistency with inaccessibility. For Aleph omega, it's a whole different story. So if you, for example, have 2 Aleph omega plus 1, and you have BC Aleph omega, then square Aleph omega has to fail. And that means that there should be inner models with, what, strong cardinals at least, or something like that. So one should expect to work hard to actually get the model of BC Aleph omega. And so we started with 2 huge cardinals, and in that we could get BC Aleph 0 and BC Aleph omega. And really what we leveraged there was that you get a version of Chang's conjecture, which allows you to go from Aleph 0 to Aleph omega. It's the only way we currently know how to do this. We don't know if all this hugeness is that necessary. So this is instances. Here and there and there you can have these versions of Borel's conjecture. Could you have it at initial segments or at big collections of cardinals? So if there's a 3 huge cardinal, then you can actually get the consistency of there's a proper class of kappas of countable cofinality at which this version of Borel's conjecture holds. And if you have 1 inaccessible, so you can get Aleph 1, and if you have countably many accessibles above it, then you can actually get all the way up to, but not including, Aleph omega. And, in all these examples so far, we had somehow built-in Borel's conjecture at the bottom to get versions or non-versions of Borel's conjecture further up. And one might wonder whether or not this version of, if Borel's conjecture is maybe implied by these others, or is necessary for these others, and it turns out that not. If you have an inaccessible, you can actually also build a model where Borel's conjecture fails, and you have BC Aleph 2. And the Aleph 2 is maybe just an artifact of the argument. One can do it for Aleph n's, individual Aleph n's. This is very recent, so I don't know how far one can take this. Okay, so a few questions. I don't know that one needs this 1 inaccessible to get BC Aleph 0 plus BC Aleph 1. One's going to need some inaccessibility, but I don't know if one needs this much. What's the exact strength of BC Aleph omega? And there's still this question in the background, what about just GBC, the global Borel conjecture? Could one, we don't know that one could have the consistency of that. We know that it will take large cardinals to get it. And there are multiple other questions, like the story about the, one could take this indeterminacy of the game, for example, and just claim indeterminacy of this game all the way up, and ask whether or not that would be equivalent to this GBC, or I suspect there are different techniques needed for that. One could take this strong measure 0 equivalence in terms of translates of G delta sets. Michael Rushak and Wolfgang Borkowski and Andrei Zendulka has recently done some quite interesting stuff about analogs of that translate property, which makes it look like it's going to be tricky to actually look at the general version of the Borel conjecture for that equivalent form. And I think I probably should stop with that. So once again, thank you for your patience.
Do we have any questions for the speaker? Let's thank our speaker again.
measurable. Continuous images of Borel sets are measurable. How about complements of those? Yeah. Continuous images of those? Then you get into undecidability. And the standard thing you do is you prove there are counterexamples if you assume P equals L, and you get theorems if you assume determinacy hypotheses. Well, you can play this game not just with measurability, but in other areas. One of the things I've done the past couple of years was looking at Menger's conjecture, which was that Menger, I'll give the definition if you don't know it yet, generalization of Lindelof, stronger property, whether this implies sigma compact, and Gruenhage showed this was true for analytic subsets of the reals. And the question is, well, what about more complicated ones, co-analytic, projective, and so forth? And sure enough, one direction using determinacy, the other direction using V equals L. So I've given a couple of talks on Menger's sigma compact definability question. And today I'm talking about another question which turns out to be extremely closely related to the first, the Menger question, although we just realized this, Stomsky and I, about a month ago. So let's get some definition. So the theme is, yes, you have the same business with V equals L and determinacy from, as you do with measurability. I'll be using projective set as a synonym for definable, but you can have more complicated definitions of definability that say results are true. So that's one theme, and the other is that if you believe in determinacy, you live on the West Coast or something, and that's fine, but determinacy has strong, large cardinal consistency strain. As I say, it's fine if you believe in it, but if you're not so sure, you prefer to prove these consistency results with weaker assumptions, and it turns out inaccessible will do. All right, so now you've heard my talk, you can leave, but I'll continue. All right, so Gruenhage proved Bear has other names, totally hereditarily Bear. All right, you can get, yeah. All right, so the two problems I show of extending these to other categories of definable sets, we show are essentially equivalent. And then there's another paper where we show that you can just make do with them accessible. And finally, a CFC result in some work that my student Chris Eagle and I did. We showed we could get something in model theory, an interesting counterexample, if we assumed a non-meager P-filter, but that's a big problem in set theory. So with Stomsky, we now have the same result in CFC. So we'll talk about that next. All right, definitions. You've probably seen the definition of Menger before. You've counted many open covers. You pick finitely many from each, and still get a cover. So strengthening of Lindelof. Completely bare. Closed subspaces of bare. Polish, separable and completely metrizable. Analytic, continuous image of the Borel set. Co-analytic, complement is analytic. Projective, mixing the class of sets of reals obtained by closing the Borel sets, actually closing the irrationals will do, under the operations of continuous image and complements. All right, so Gruenhage, analytic Menger subsets of the reals are sigma compact. So problem one are definable, whatever that means, Menger subsets of the reals sigma compact. fact. Co-analytic, completely bare subsets of R are Polish. Definable, completely bare subsets of R Polish. And you do have to throw in some sort of definability because there are counterexamples if you do non-constructive stuff with the accent of choice. All right, so previous researchers, Miller and Fremlin, for the Menger one, did, as I said before, determinicity V equals L, and for the completely bare problem, one direction is an exercise in Kepler's book, I'm not sure who did it first, and the other direction, getting a counterexample under V equals L, is 2015 with Dini and Domsky. Okay. Here is an axiom you may not have seen before, and it's called OGA star of gamma. OGA, which stands for open graph axiom, used to be called by Stavo open coloring axiom, but this was a cause of confusion because that name had been patented earlier by Abraham, Rubin, and Shalaf for something different. So when a referee suggested that Stavo change the name to open graph axiom, he took up that as a good idea. Okay, the open graph axiom, instead of having a perfect set here, you have an uncountable set. So you may have seen this before, as I say, in Stavo's partition problems in topology book, and elsewhere as the open coloring axiom. You partition the two element subsets of X, given topology inherited from X cross X. Then either there's a perfect set which is homogeneous for one part of the partition, or X is the union of countably many sets, each homogeneous for the second part. Now, Chi Feng, 1993, introduced this variant of it, which is due to Stavo, and calling for perfect rather than uncountable. What's somewhat unintuitive is that, and here you're restricted to a particular collection of subsets of the real projective sets, for example. What's somewhat unintuitive is that OGA star of gamma does not imply OGA, because you can get a model of this and say OGA star projective in which CH holds, but the open graph axiom implies not CH. So these things are different.
Well, but I mean, this only makes sense in the absence of choice.
No, not if you have.
Look, OGA star is a stronger statement if you talk about gamma being all of the powers of the reals. Which is,
Yeah, no,
which
I'm
is
not
the only
doing
context in which you talk about OGA.
Wait a minute, I'm talking about this in the context of projective sets, for example, and then the usual open coloring axiom talks about sets of reals, yeah.
Yeah.
But
But if you take OGA, but just for projective sets, that's a weaker statement.
not weaker than the usual open coloring axiom.
Weaker than this.
Right? It's OGA star gamma is a stronger statement than OGA gamma.
Yes, but not a stronger statement than OGA, period, without the gamma.
Yeah, right. But OGA star is also something which people talk about, but it only makes sense in the absence of choice. Your statement about CH is just kind of a strange one in the context of choice, right? Because
I don't.
Go ahead.
All right, we'll talk about that later. Okay, so Stomsky, we proved putting together new results and old ones of phone or bridge. The following are equivalent. Co-analytic Menger subsets of R are sigma compact. Then the other problem, analytic completely bare subsets of R are Polish. For every real, omega 1 in the sense of L of A, the universe constructed from L of A is less than omega 1, and the OGA star of co-analytic, and every uncountable co-analytic set includes a perfect set. All right. No point in going through all the details here, but see if the last three were proved equivalent by phone in 1993, and that A implies C and B implies A are in a paper of myself, Stavo, and Sekshi Togos, which is not in final form when the referee came back. It has to be rewritten. And the new results then are in Paul and Stomsky, which is in process. And essentially, the variation of this is an equally consistency result, that the following are all equally consistent. Projective Menger subsets of the reals are sigma compact. Projective, completely bare subsets of the reals are Polish. There's an inaccessible cardinal, OGA star of projective, and every uncountable projective set contains a perfect set. I should say includes a perfect set, right, Alan?
Yes.
So this is proved by the same methods as the previous theorem. Just note that saying that omega 1 in the sense of L of A less than omega 1 implies omega 1 is inaccessible in L, so that gives you consistency of an inaccessible cardinal. And then Fung showed that collapsing an inaccessible to omega 1 in finite conditions produces a model in which OGA star projective holds. Okay. It's a very nice result of Hurevich, 1928, that says a set of reals is completely bare if and only if it doesn't include a closed copy of the space of rationals. The only place I know that has a proof of this in English is Jan van Mil's function space book. And this is the surprising thing that connects Menger to completely bare. If you have a Menger subspace, actually of the reals will do, then its complement is completely bare. And the reason is, if you're not complete, if you're you have the complement of X not being completely bare, then you have a copy of the rationals, which is closed in K minus X. Then the closure of that in compacts of K has intersection with X homeomorphic to the space of irrationals. But that closure intersects X, is closed in X. Closed subspaces, Menger spaces are Menger, and the irrationals are not Menger, so you get contradiction. Despite the close connection here of completely bare complements with Menger, it's not an if and only if, because if you take a Bernstein set, both it and its complement are completely bare, but they're certainly not Menger. All right, so why does this hold? proved it held. You can, I'll skip this. This shows that you can play around with perfect maps and prove it for R minus X, not just K minus X. All right. If you have a co-analytic Menger and not single compact set, then its complement is going to be analytic, completely bare, and not Polish. So there's that connection between the two. The way you do the other simple ones in that equivalence are, you basically show that that A implies C, which Meng showed implied D, and then the hard part is showing that this OGA star business implies this Hurewicz dichotomy about getting the rationals on one side and the irrationals on the other. That's the only difficult proof. And from that, you get whether A or B or whatever you like. Yes, that's what I'm saying here. You get this Hurewicz dichotomy that's in the from OGA star of gamma. That's in paper Stavo, and then that follows easily. If you have something which is analytic and completely bare, it must be Polish. But if it's not Polish, its complement is not single compact. Therefore, you have this compact set, which has intersection homomorphic to the rationals, but that's closed in B, so B can't be completely bare. So the Hurewicz dichotomy is the key to all of these. Yeah, so one of the reasons I was interested in this, my student Chris Eagle and I, there's an important theorem of model theory called the emitting types theorem. And people, model theorists have always said, well, this is like bare category, and just like bare category theorem is a weakening, a useful weakening of the compactness theorem, space-being compactness topology. The omitting types theorem is a weakening of the compactness theorem of first-order logic that is useful when you don't have compactness around. So this was sort of everybody knows type of thing, and there were proofs of the omitting types theorem using the bare category theorem, but the exact relationship of the two was not known, not clear, so we decided to investigate this. And the investigation turned out to be quite interesting. For one thing, it turned out it was not the bare category theorem, it was the assertion that closed subspaces all satisfy the bare category theorem, i.e. completely bare. That was what was involved here. And bare category wasn't enough, and you actually can write down a theorem saying this omitting types theorem is equivalent to closed sets satisfying bare category theorem. The reason, of course, logicians didn't realize this is because the logics they dealt with were sufficiently simple that the associated topological spaces were all locally compact or completely metrizable or whatever, and closed sets inherited the bare property there. So one thing we did, and this builds on work you can trace all the way back to Morley, but most recently by that there is a machine that converts arbitrary, I stress the word arbitrary because this is new, arbitrary topological spaces into logics. For every topological space, you can define an abstract logic. Now, there's the minor detail that there aren't any formulas, but Shalot did this already with his abstract elementary classes, so it's good enough for him, it's good enough for us. And the beauty of this is model theory doesn't have that many examples, but set theoretic topology is crawling with all sorts of weird pathologies coming out from under rocks. And so you can bring these into model theory. And as a particular example of this, this omitting types theorem, which is like bare category, well, we know bare category is having somebody not having a winning strategy in the Banach-Mazur game, and there's this stronger property, weakly alpha favorable, in which the other side does have a winning strategy. So you can play the same games here and strengthen the omitting types theorem to say there's a game you can play and somebody has a winning strategy. Now, natural question arises, okay, is this real strengthening or not? And it isn't first order logic, you can prove that the two are equivalent, but we, using topological examples, we saw that we might be able to get a counterexample of constructive logic in which these two were not the same. And our first attempt well, first of all, we showed there is an abstract logic satisfying the omitting types theorem, but not the game version if there's a separable metrizable space such that its countable power is completely bare, but it doesn't include a dense completely metrizable subspace. So we asked around, nobody knew such a thing, so we had to construct it. And thanks to Zdomsky, we found that if you take a non-meager p-filter, the existence of which is a long open problem in set theory, the filter itself is an example of such a space. Well, but you need such a strong hypothesis. No. Zdomsky pointed out that a result of his with Repoffs and Zhang says that there's a subspace x is 2 to the omega, such x is meager, non-meager, is a filter extending the Frechet filter, and it turns out that also gives you such a space, and therefore gives you such a logic. So that's the good result. And I go ahead and do the proof here, but I don't have time, so thank you very much.
Are there any questions for the speaker?
I have one. You mentioned like, okay, yeah, this extends for other things, accountability. I'm assuming you kind of meant from like PDA or other things like that.
Definable for real.
Define number. Oh, okay. Well, I'm just curious because like you mentioned this tradition, and there's some interesting stuff that like Shalot, where he does it for like co-composition sets specifically instead of projecting.
Yeah, okay, that's an interesting question. You see, I did some work with Senchikogos on extending this consistency of coanalytic member replacing compact to spaces that were not just several metrizable, and we got some results on that.
Yeah.
And it is a very natural question. All right, it's currently fashionable to do descriptive set theory on kappa to kappa instead of omega to omega, and so the question is, all right, make the appropriate definitions of coanalytic, Menger, etc. Do you get analogous results there? And the answer is, I haven't tried it. It's an interesting question. Please look at it.
Any more questions? Speaker again.
Right.
Test that, make sure that's working on.
But if you're starting to.
Yeah, just right and left.
So for the next slide, I push this
Yeah, see that.
on the side. Okay, let's see. Where do I point it there?
It doesn't matter.
Oh, okay.
Just right and left. You can point wherever you want. It's all good.
Well, for the point that it's on.
What is this button here?
You can. It's a joystick. You just go right and left.
Oh,
There's no laser range.
We'll talk about classic problems 3.
Well, it gives me great pleasure to be here, and especially to be able to talk about some of Gary Gruenhage's accomplishments. I've known Gary since, 24 years. 24 years I've known him. He sent me a letter, a very nice letter about some ideas he had, and out of that ultimately came a very nice joint paper, the two of us, and we've been good friends ever since his first letter, actually, and so I'll be talking about some of those.
Peter, that was a lot longer than 24 years.
Oh, 44 years. Sorry, yeah. Way back, 1973. Yes, thank you. All right, so before I start, I want to put in a good word for this book, Open Problems in Topology #2. If you don't have it, at least take a look at it, because this should give you a number of ideas for research, and if you solve one of the more important problems in here, you're well on your way to fame within a group like this. Okay, so I'm going to change the order a little bit on these problems. This is problem 10, classic problem 10, and then I'll get back to classic problem 9. Gary has done some really nice work on this, and especially on this variation. So the question is, does there exist a perfectly normal, locally connected, locally compact space that is not metrizable? Well, Mary Ellen Rudin asked this question, and it's, about 35 years ago, and it has still not been solved. There are many examples under various separate hypotheses, but whenever I say, does there exist, I'm asking, does there exist in ZFC? So the two most interesting answers are, yes, there does, and no, there's this model where it fails. But also it's interesting to have more and more examples of models where the answer is yes. Okay, so if you continuum replaces locally compact with compact, and that makes a different problem, but actually the two problems are equivalent under Martin's axiom, and I'll get around to that in just a little bit. Is there T6 means perfectly normal, I use that from now on. Locally connected continuum, meaning compact connected Hausdorff space that is not metrizable. And in this book, Gary has a joint paper with Justin Moore in which you can read about this quite a bit. It explains how powerful trichotomy axiom was formulated by Gary. If it's consistent, we don't know whether it's consistent, then there's a negative answer to problem A. And so, therefore, well, not the problem axiom. That's a different problem. Anyway, I'm calling this Gruenhage's axiom, even though we don't know whether it's consistent, because it's such a nice axiom. And besides, we have a precedent set by Rothberger in which he formulated an axiom that very strongly negated the continuum hypothesis, but he went ahead and did things with it. So here we go. Every uncountable regular first countable space contains either an uncountable discrete subspace, an uncountable subspace of the reals, or an uncountable subspace of the Sorgenfrey line. And that's a very interesting question. Okay, so now I repeat the classic problem 10 and also A. Here's some consistency results. If you assume the continuum hypothesis, Merrill and Rudin constructed a perfectly normal non-metrizable manifold. And Gary Gruenhage relaxed the continuum hypothesis to the existence of a losing set. Filipov showed that a losing set also gives an example for related problem A. That's the locally connected continuum, but that was definitely not a manifold. And the Sussman continuum also gives a negative answer. So, CH gives you one thing, MA plus not CH implies every perfectly normal, locally compact, locally connected space is paracompact. This is a result of Diane Lane, who got her PhD here at Auburn University back in 1977 or thereabouts, 78 maybe?
Something like that.
Something like that. Anyway, there's a few standard tricks that should show you that the problem 10 and related problem A are equivalent under MA. The tricks are this. Locally compact, paracompact spaces are topological direct sum of Lindelof subspaces. Now you take each of those perfectly normal Lindelof subspaces. By the way, perfectly normal Lindelof is equivalent to hereditarily Lindelof for all regular spaces. So you add 1 point, it's still perfectly normal in Lindelof. Well, then it becomes Lindelof, then it becomes compact. And then you've got these compact spaces, topological direct sum, and, well, that's how you get the two problems equivalent under MA. Gary generalizes Lane's result by showing that every perfectly normal, locally compact, collection-wise Hausdorff space is paracompact. And there's a trick to here. There's a nice little result that every perfectly normal, locally compact, locally connected space is collection-wise Hausdorff. And so then you get this being a generalization. And here's where he showed it, Russian Mathematical Surveys. Okay, two more related problems. Is there a perfectly normal, non-metrizable, generalized manifold in the sense of Wilder or in the sense of Alexandrov-Czech? Every generalized manifold in either of those two senses is perfectly normal, locally compact, and locally connected. So a negative answer to the classic problem would also settle the 1949 Wilder problem, and a negative 1 to A would also settle the 1935 Alexandrov-Czech problem, which required compactness and not just local compactness. And by the way, both Filipov's Luzin set example and the Sussman continuum are consistent examples for problem B. But what may need to be done is for somebody to get together with some algebraic topologists and geometric topologists, look at those extra things that make something a generalized manifold, and maybe those will eventually together with some set theoretic techniques, I hope, eventually settle problem B. But again, Gary Gruenhage's axiom, if it's consistent, would also settle it. Okay, so of course, C is every perfectly normal locally connected continuum of weight less than or equal to A lift 1. And CH implies a yes answer, obviously. But here's the thing, manifolds won't work for C. Well, they don't also work for B either, for reasons given here. Every Lindelof Euclidean manifold is of countable weight, hence metrizable. So Euclidean manifold would not work for problem C, and it wouldn't work for problem B because every perfectly normal Euclidean manifold is metrizable under MA plus not CH. That result, last result, was due to Mary Ellen Rudin in 1978, and you can also get it from Diane Lane's generalization and Gary Gruenhage's yet another generalization. One more thing to which Gary contributed. Is there a perfectly normal, locally connected continuum that is one not arcwise connected or contains no arc? Well, if you, this is stronger than just that classic problem, related problem A. Gary showed that CH implies there is a perfectly normal, locally connected continuum that is not arcwise connected. And that gives a consistent example to the first part, and there it is, right in Topology and its applications way back in 1990. All right, now here we come to the number 9. Is every point of omega star, the Stone-Check remainder of the integers, a butterfly point? And a butterfly point is very easy to visualize. Here you have these two closed sets. Is every non-isolated point of beta omega a butterfly point of beta omega? That's pretty easy to see that it's equivalent. This one's a little harder to see. Is beta omega minus p non-normal for every non-isolated point p? But when you get to here, it's a different problem. Even if you show this, you might not be able to show this. But vice versa, look in omega star. If you take away this point, if what the resulting thing is not normal, well, you've got to have two disjoint closed sets that just, well, they both have to have that extra point in the closure, and that any closed sets that you cannot separate by open sets would have to behave like this. So butterfly point is the first step towards showing non-normality. And then a yes answer to the main question is implied by this reaping number being equal to C. If in addition you have two less than cofinality C equals C, then you also have a yes answer to A. Problem B, obviously, if you do have this thing being normal for some P, then you've got yourself a normal countably compact, non-compact subspace in beta omega. But I don't know of any consistent results either way for problem B. Of course, any model with a negative answer to A, like I just said, will give a consistent example for B. Next, is there a normal space with a sigma disjoint base that is non-paracompact? You will find that question in this book, briefly talked about by Paul Sheptitsky. But then there's two others which I haven't seen anywhere, but they're very logically weakenings of this classic problem 11, because if you have a normal space with a sigma disjoint base that is not paracompact, it will be a Dowker space. And so now you weaken sigma disjoint to sigma point finite, sigma point finite to point countable. By the way, a Dowker space is a normal space that is not countably paracompact. But the nice way to tell it to anybody who's not a set theoretic topologist, it's a normal space whose product with a closed unit interval is not normal. Anyway, the reason those are weakenings is this. 1955, Nagami showed that a space is paracompact if and only if it is normal, countably paracompact, and screenable. And that means every open cover has a sigma disjoint open refinement. And since spaces with sigma disjoint bases are obviously screenable, this is asking for a Dowker space. Now, repeating that one, it doesn't mention countably paracompact, so let's just weaken sigma disjoint and see what we get. Is there a normal space with a sigma point finite base that is not paracompact? And then same thing with point countable base. Now there we have some consistency results, and these two problems split naturally. If the space is countably paracompact, it's a solution to A or B. But if it is not, but if it is countably paracompact, then it's a whole new ballgame. And so here's why. Every normal Moore space is countably paracompact. Every normal metacompact Moore space has a sigma point finite base. Similarly, every normal Neff-Lindelof space has a point countable. In fact, I don't even need normal. Every Neff-Lindelof Moore space has a point countable base, and I don't need normal for the other one either. But of course, these are asking for normal spaces, and they do exist if P is greater than A of 1, and also if the covering lemma holds over the core model, because Bill Fleissner's example is countably metacompact. Metacompact. And so, so that's, you need large particle axioms to negate this, but we still don't know whether, in this case, well, of course, Moore spaces won't work, but maybe some other normal spaces will work. Okay. No consistency exact results on either of the following problem or its listed related problems. Is there a regular symmetrizable space with a non-G point? Symmetrizable space is a space in which you have a distance function which is symmetrical but not transitive, and it's also reflexive, and a set is closed if and only if every point outside of it is at a positive distance from it. Well, Gary produced a regular symmetrizable space with a non-G delta closed subset. Now that was already an old problem due to Ernie Michael. He also wanted a non-G delta point. Well, Gary got a non-G delta closed subset, and this is a joint paper that I'm very proud of. And this statement here, I'm not so sure of. I talked with Sheldon about this. Gary's space was not normal. That much is true, but I don't know whether just collapsing that closed set to a point is going to get you anything useful. We'll have to talk about that some more. Well, this was in 1978 that three of us were working together just perfectly. I mean, what Sheldon Davis kept telling us, if you want such and such a thing, well, these are some of the properties it's going to have. And that really helped us to focus our thinking. But even so, this example of Gary's is one of those examples, like some of the examples of Marilyn Rudin or Zoli Bolog. I look at it, I have no idea how he got the idea for it. But anyway, now what happens if we do ask for normality? Well, it would get us probably be a stronger problem. And so there's one. Now, if you have a B, symmetrizable Doppler space, then what you have is a descending sequence of closed sets whose intersection is non-empty, but you can't follow them down by disjoint open sets. If you add one point in the right way, you're going to get a normal symmetrizable space with a non-G delta point. I tried this trick. There's a special way of doing this, and I did it with Gary's space, but I wasn't able to preserve regularity. We have a Hausdorff space with a symmetrizable Hausdorff space with a non-G delta point, but a regular one is going to be a lot harder to get. And the one thing I want to mention about this example is that besides the one closed set that Gary found, there were countably many others that were disjoint from it, and the union was closed. There were a discrete collection of closed sets. So the trick was you add one point, and then you just subtract off the first n of these, and then you've got yourself an example which is Hausdorff and has a non-G delta point, but the problem is you lose regularity, whereas if you do the same thing for normality, the sets have to be different. You have to be able to, well, there will be a situation where the very first set is not closed, but it actually has every other thing in its closure. You're taking away, the next one is going to have everything in its closure and so on. And those kinds of non-metacompact spaces are much harder to get than the ones where you just have a discrete collection of closed sets that cannot be expanded to a point finite collection. Okay, that's it.
Are there any questions for our speaker?
I presume the Doppler space questions, none of Ballow's examples have those properties.
Right. Yeah, oh, by the way,
And the follow-up question, I assume also Ballow didn't think about those particular questions, otherwise he would have probably.
Oh, he did think about that.
Oh, he did?
oh, he did. He definitely did. In fact,
The point, you mean the point finite and the
sigma
point
disjoint. Well, I don't know about the point sigma point finite in that. He thought he actually had a normal space with a sigma disjoint space that was not paracompact. He was about to talk about it at Slippery Rock. He was one of the invited 1-hour speakers, and I went up to him about 10 minutes before the talk began, and I said, look, I don't see how you're able to do this because, well, you're mixing these ends and so on. And he looked at it for about, well, 2-3 minutes, and then he decided it was wrong. He got up in front of the audience and said, I thought I had an example. I don't have one, so now you have a free hour.
Any other questions for our speaker? Comments? All right, let's thank Peter again. So in 7 minutes, you have a coffee break.
Nobody minds if you're over.
So free 7 minutes.
Our next speaker will be at 11. Welcome to the second session of this morning's conference. Right now we have Todd Eisworth, who will be talking on the revised GCH.
Hi everyone, thanks for showing up. I was working on abstract my spiritual self. I wanted to start giving some background of my own interactions with Gary. Probably the most important thing is dialing back about 20 years or so, young guy starting out. I didn't originally start doing Egyptology, and I found myself kind of gravitating towards that. Felt kind of like I had found a home, a community. And Gary has been a large part of that. Just one of the very first people I met in topology. There are lots of others now, tons of folks. But that made a big difference for me. And I just wanted to kind of acknowledge that all you guys are great. Thanks. Now, it's kind of a talk where either everybody gets something out of it or nobody's going to learn anything. We'll see which way it comes out. I promise that what I'm talking about today is kind of got a topological inspiration on it. All the big ideas I'm going to talk about are due to Saharan. I guess what I've been involved with the past couple of years is I've got a grad student very interested in PCF theory and stuff. So we've gone back and looked at a lot of papers that I read 20 years ago. And I guess it's been a little bit gratifying because as I go through them now, I find myself, instead of saying, why did he do that? It's more like, well, why didn't he do that instead? Which is progress. So this is what resulted from, well, why didn't he do this instead? Maybe something understandable. So basically we're talking about some resulting cardinal arithmetic. Start here with, I guess, the definition of lambda to the revised power of kappa. It's a way of measuring the size of the subsets of lambda of size kappa. And it's kind of like a covering property. So we're asking for the minimum cardinality of a family of kappa-sized subsets of lambda such that any kappa-sized subset of lambda is captured by a relatively small unit. Okay? Now what could that be useful for? Well, it turns out there's a big theorem lurking in the background here. Shalaw's revised GCH that says very many situations you're going to have lambda to the revised power of kappa equal to lambda. So that there's a small, relatively small family of kappa-sized subsets of lambda that captures them all. Now, there's some hypotheses here, right? It starts off with a weird, let mu be uncountable strong limit. Then for all sufficiently large kappa less than mu, we're going to have lambda to the revised power of kappa is equal to lambda. So it won't be for everything, but eventually. And you'll see this most often applied in the case where mu is Beth omega, the first strong limit cardinal. Now, as a corollary, if you close up under power sets, families got to really capture subsets of lambda. I mean, we can generally, given any small subset of lambda, we can write it as a union of fewer than kappa many members of our family P. This kind of explains the name. If you think about a pair kappa less than lambda, then GCH is equivalent to lambda to the kappa is equal to lambda for all digits.
So in the second sentence, how do you quantify the kappa? Does there exist a kappa less?
For all sufficiently large regular kappa less than mu. So you can pick the least numbers.
I mean, if you read it, it's saying, okay, there's a family. Oh, okay.
Yeah, so it's just more generally that you can, by closing up under power sets and subsets and stuff.
But this would just be the same as saying that, that it's a union of strictly fewer than mu many, right?
Yeah, well, you're going to, it's lambda, yeah, so, yeah, exactly right, because we'll see where there's a strong limit. The point is, regular GCH says for pairs kappa less than lambda, lambda to the kappa is equal to lambda. Revised GCH says that for most pairs kappa lambda, lambda to the revised power kappa is equal to lambda. So, I mean, Saharan has a very eloquent argument where he says that this should count as solving Hilbert's first problem in a sense. Very nice.
You really mean to say equal to a union or
Yes.
just covered by?
Well, because we use strong limit, we can pass to subsets of it and actually get an actual equal to it. And that turns out to be where it has some strong applications. The connection to topology, I just pulled out some, these are all due to Saharan, but some nice applications. Maybe we'll talk about the first one for a second. The revised GCH put some restrictions on the sizes of generalized almost just joint families. And this is how I got involved with revised GCH, because that first principle is connected to the old problem in topology of whether every topological space can be partitioned into two pieces, neither of which contains a copy of counter space. All right, so this turns out to be an ingredient in ruling out, or getting a yes answer in very many cases, and showing that a no answer, or consistency of a space that doesn't have such a partition, requires some heavy machinery. You see, it's, at this point, all the best applications I think are due to Saharan, which is maybe one point out of this talk is that you'll see a little bit about what's going on with it. So, here from Beth will maybe down all the fold. It's a natural question to ask about the role of the strong limit seems to be part of it. Can we instead just get some version of this that holds with mu just being a singular cardinal? And yeah, Saharan had produced what you might call the PCF theory core of the revised GCH. We'll talk a little bit about what these things mean. But the point here is, the takeaway is that there is a version of this that, under certain hypotheses, produces, I guess technically that's probably a weaker conclusion. Now look, this implies revised GCH because if you use a strong limit, the assumption holds. And you can, given this, given the corollary, you can milk out the conclusion of revised GCH as well. So take a look at, this is a version of revised GCH that doesn't have any assumptions about the power set to the sigma for various sigmas. Something for everyone here. I'm not going to need a lot of PCF theory. I do need kind of the basic definition. Given a set of regular cardinals and an ideal on it, we'll say that we have true cofinality equal to lambda if there's a lambda scale. So increasing mod lambda sequence of functions, increasing mod j sequence of functions of weak lambda that dominates everything in the product of A mod j. And the point is, you may not get a true cofinality, but you always do when j is a maximal ideal. And that's usually how PCF A is defined. It's a set of true cofinalities that arise. Now, if I back up, the reason I'm expressing things this time is I had something here that said PCF sigma complete A. And what that means is that you're looking at true cofinalities where the ideal J is required to be sigma complete, which is, well, there are going to be fewer of those. But this is going to be generally smaller than PCF-A. But it's a needed parameter in what we're going to talk about. So maybe before I get into the proof. Saharan did a perfectly nice proof of this theorem. The only issue I have with it is that the proof literally starts out with a sentence that says, for simplicity, assume there's a Ramsey cardinal in the core model Ka for every subset A of 2. Okay. I just can't even. You don't really need, that's kind of a red herring, because what he really needs is he's using some exotic notions of rank for functions, ordinal value functions, and that in order for them to be defined, you need to have some large cardinals in the background. If you leave them out, the proof gets harder and you don't get everything you want, but it's a big deal, but it just kind of felt like we ought to be able to do something else. And that's where the topology comes in, because so reading through it, I kind of realized that what's going on is one of the very first general topology exercises I can remember solving is that if you got a countably compact space X and you remove a point and you find a closed discrete subset of the remainder, that's got to converge to the point you just removed, right? So that is the big idea that I want to implement here to prove it. Now, of course, there's going to be a lot swept under the rug. When I say looking for a simpler proof, I'm really saying if somebody's gone through the Handbook of Set Theory chapter on PCF theory, limited to those tools, get a proof that works. Again, I'm going to keep things, I hope, sufficiently vague. The theorem fails for a limit, singular limit mu. Then, without this generality, the first lambda that causes problems is singular cofinality omega. And here's the thing. The failure of that revised GCH implies that there's going to be arbitrarily large cardinals less than mu, with the property that you can find a sequence, length theta, and a theta complete ideal such that the product of that sequence modulo the ideal has true cofinality lambda plus. So it's like you can get worse and worse ways of sequences converging to lambda plus. They're longer and the ideal is more and more complete. So this happens for arbitrarily large theta less than mu, and I'm calling the set of places where that happens R. It's going to come up, but that's what we're going to use to generate the contradiction. You want to think about it in terms of convergence if you want. True cofinality equal to lambda plus, I mentally always think that means the sequence converges to lambda plus in some sense. So we're going to start by taking an uncountable cardinal in R and fixing a sequence of cardinals in a kappa complete ideal so that the sequence converges to lambda plus, and we are going to build another sequence with a property that we've dropped down almost everywhere, measured by the ideal, but we still keep the convergence to lambda plus. Why is that a problem? Well, run this countably many times, you generate a countable decreasing sequence of things mod I, and I is countably complete. That's going to yield a contradiction, but you're going to get a countably decreasing sequence of ordinals. So this is impossible. What I'm going to do is try and produce a sequence of psi i's that still converges mod I to lambda plus by dropping down. And this is that idea of removing a point, and I'm going to find a sequence, and well, it's got to converge to the point I removed, is how we're going to make this work. So, assume for sanity's sake. The way this works in reality is that given my sequence of lambda i's, I need to break it up into different pieces and work on separately on each piece, and then paste everything back together to get my sequence of psi i's. I'm not willing to do that for you today. But we're going to assume, well, let's think about it. Lambda is supposed to be the least counterexample to the revised GCH at mu. That means if I drop down, which my lambda i's are less than lambda, revised GCH is going to hold, which means that there's going to be some sigma that works for lambda I in the statement of revised GCH. I'm going to assume I've got a sigma that works for all of our lambda i's. Just take it.
Sigma that counts.
Yeah. Well, it is kind of, well, we have to do countable anyway because the cofinality of mu is countable, but. So right, our assumption on mu, remember, is that if a set of regular cardinals has cardinality less than mu, then cardinality PCF is less than mu. And it's not hard to see that that means if I bound the cardinalities of the A's I'm looking for, the PCFs have got to be uniformly bounded, or else we can paste them together to get a counterexample, to violate the hypothesis of being. So I'm going to fix a theta in R, have arbitrarily large less than mu, such that this happens, and I'm going to fix a sequence in an ideal witnessing that theta is in R. Now, I will admit that I had slide envy yesterday watching Will's graphics. So this is mine. What I want to visualize here is a giant matrix. Along the top is our sequence of lambda i's, or kappa many of them, and they converge to lambda plus mod R ideal. And running at the side, the sequence I just fixed, it's longer, theta is much longer. And then in the middle, I'm going to use a little PCF theory to say that I can find a sequence of tals for each zeta that converges modulo I, the ideal along the top, to chi sub zeta. So we've got some horizontal convergence to the sequence across. All right, that's not hard, but kind of just need you to have a picture. We've got, along the edges, we've got sequences going to lambda plus, and in the middle, we've got sequences that are, it's critical they're using the same ideal I'm using on the top sequence, converging to these pieces. Because what I'm going to do is kind of think topologically. What I'm going to show is that this setup is going to make it possible to generate a sequence of psi i's that run away and have to converge to lambda plus. Let's get ourselves grounded. Column I is a sequence of cardinals between u and lambda I. PCF sigma complete for column I is a subset of lambda I because, well, we just sigma worked for lambda I. So if I take PCF sigma complete along any column, I don't jump out the top. So what I'm going to do is I'm going to let A be the collection of cardinals making up the matrix, the tals, and take PCF of it. You know, I can, by making some of the tals equal to B plus, I can arrange that the maximum value of PCF A is going to be equal to lambda plus. We don't get anything bigger. That's just the changes you would need to make to accomplish that don't interfere with the structure. And I've got a set of less than fewer than mu many cardinals. It's at most data by kappa. A star is set up for some PCF theory, and I can pull out a set of nice generators for psi and PCF. Now, one thing about these generators is kind of like an open set. For any psi and PCF A, there's going to be a corresponding generator, B psi. It's going to have psi as its max, and it's going to have some orbitals that are down below it. And the way it works like open sets is that if you hit that open set too much, you're going to pick up psi in your closure when you take PCF. So if I want to avoid picking up something in my PCF, I've got to build a sequence that kind of misses each of some generators. This is, I guess, one bit of advanced PCF I need is that I can arrange, because I'm in a nice situation, I can arrange my generators nice and organized. So if tau is an element of B psi, then B tau is a subset of B psi. Right? It's going to be important later for the contradiction. All right, key point. This is where I wanted to make sure I got. Think about my matrix. Remember, I've got lambda i's across the top, chi sub zeta's up the side, and then my rows. My rows are converging this way. If I'm given an element of PCF-A, something that can be raised a true cofinality of a product of those tau sub i's, and it's less than lambda, not lambda plus, then its generator has got to hit that matrix in a very small way. And the idea here, this says that the set of rows where I picked up I positively many tau sub i's has got to be small as measured in terms of j. And the reason being is that if I pick up a relatively large set of a row, I'm going to pick up its limit when I take PCF. And if I pick up too many of those, I'm going to pick up lambda plus in my limit. So this is saying that the generators I'm looking at meet the matrix in a very small way. Okay? Now, this is where I'm going to use the fact that we're theta complete alongside. If I'm given a small collection of PCF-A, small being less than size theta, then eventually, almost every zeta star is going to have row zeta star meet these B chi's in a small set. Right? That's just the completeness of the ideal I'm working with. So, you know, we've got a row zeta star that's going to run away from all the generators, all the open sets associated with this small collection. Okay? And now we've got to choose this guy very carefully. to make things work out. So that's the picture. I'm using a row that runs away from, given a small subset of PCFA, I can find a row that runs away from all their open sets. I'll wave my hands here. We're going to apply the previous statement to a special collection D. And what I'm going to do is in each column, you know, I know that PCF of this, sigma complete PCF of this column is contained in the top. One of the, I think someone used what's called compactness of PCF generators to say that there's going to be a set of, in a given column, I can find fewer than sigma leading elements of PCF sigma complete of the column, whose generators cover the column. So this column is going to be covered by finitely many of these open sets. And there are not too many of them. And if I throw in a few things from each column, union them all up, I've got a collection of fewer than sigma many elements of PCFA. I get PCF on that. By choice of theta, I know the PCF has to be less than theta. Theta was chosen so that if I took a set of size less than sigma and took its PCF, the cardinality is less than theta. So this gives me something where I can run away from D by the previous thing, about a small collection of things in PCFA. I'll find a row that runs away from that. Now, let's go up to our magic row. Okay? Each element of that row is covered by one of the generators we picked to cover that entire column. So let psi I be the element of PCF of the column whose generator covered that entry in the row. I claim that that sequence of psi i's I've generated is going to run away and have to converge to lambda plus. And by our choice, since we were applying our induction hypothesis on each lambda i's, the psi i's are all less than lambda I. And of course the point is, this is where the niceness of the generators comes in. If I'm given something in D, PCF of C, if I'm an element of B chi, then tie zeta star bi is also an element of B chi. And that's because of niceness. That means there can't be too many places where psi I is an element of B chi, because there are too many tau zeta stars that are element of that. The point is, I've got a generated sequence of things in C that run away from everything in PCFC that's less than lambda. There aren't too many of those. And I've chosen my column, my row high enough to make sure the row ran away. Transitivity of generators means that the psi i's themselves have to run away. And then you're left with just using some PCF arguments saying, well, essentially we're dealing with a countably compact space. It's got to have some sort of limit. Lambda star is the unique limit, and then it's hop, skip, and a jump to getting to lambda is actually the true cofinality of those guys. And that's going to generate your contradiction. You've taken the sequence of lambda i's and lowered them, and still converge to lambda plus. And the fact that an I is countably complete means that that can't happen. And I think I'm done.
Are there any questions for the speaker? Okay, let's thank Todd again.
Thanks.
Right, so for our last talk in this morning's session, let's welcome Paul Gartside, who will be speaking on diversity of the freewheeling group.
Thank you. It's a great pleasure to be here. Great to see you again, Gary. Just want to mention that I had some dental work, had some problems earlier in the week, so my voice may be a little fuzzy. I'll try to speak up. Let's hope it goes. Okay, so actually the title wasn't completely accurate, so I'm interested in the free abelian topological group. So I'm interested in the topology there. Basic setup is that we have a set X. A of X is the unique free abelian group containing X as a generator, so that the natural way that we can extend a function from the set X into any abelian group, it has a unique extension. Okay, and the topology part is that we play the same game again, but instead of looking at functions from the set X into an abelian group, we look at continuous function maps from a space into an abelian topological group, and what we do is we insist that the extension has to be continuous as well. Okay, and the point that I want to make here is that this definition of the topology is as a universal property. It's non-constructive, so it's just something which happens, and potentially we're looking at maps from the space X into a completely arbitrary abelian topological group, and we don't know what they are. And so in some sense we don't entirely know what the topology is. It's a little bit like the stone check compactification. It's a very large, complex object. Or at least the topology is. The set's just itself. It's just the set in the group case is exactly the same as the set topological case. Okay, and what I want to do is to talk about how we can understand the diversity of free abelian topological groups. And to do this, I'm going to talk about something which I've talked a lot about recently. I'm trying to make sure this will be about the last one on this topic. So I'm going to do the first part of the talk quite quickly so I can get on to more recent work. But the setup is that we're going to be looking at directed sets. I'm particularly interested in this scenario in neighborhood filters. So we're going to look at a neighborhood filter of 0 in my free abelian topological group. And we're going to think about this as an ordered set and set inclusion. So just to remind you, N, the sequences of natural numbers. Cofinal sets, cofinalities, D is the cofinality of N to the N. These are all things you know, so I'm not going to spend any time on. Let's move on to things which are less well known. So less well known is what do the neighborhoods of 0 look like in the abelian topological group? What is the shape? How can we describe the order structure of this? What's the cofinality, in other words, the character? And the basic problem is that because we have no good handle on the topology on free abelian topological groups, it's very difficult to try to distinguish between different free abelian topological groups, even when the space X is very small. So what we're going to see today is that we're going to see a way of distinguishing between them using the Tukey order. And then I'm going to move over to even smaller spaces, so compact metric spaces, continua, one-dimensional continua, things like that. All right, so let's start with the bigger, smaller spaces. So,
Excuse me, N sub 0, is that
it's the neighborhood filter.
bare category 1 sets?
No.
Rieger sets? No?
The neighborhood filter of the unit element,
Oh, okay.
0.
Early N stands for neighborhoods in this context. Subscript stands for the set around which we're doing the neighborhoods, and we're going to do points. So we're going to look at the 0 element. Superscript is the space in which we're doing neighborhoods. So we're looking at the neighborhood filter of 0 in free abelian topological group. Okay, so the setup is that despite the gloom and doom I was spreading earlier about the topology in the free abelian topological group being so non-constructive, there's lovely work by Nicholas and Karchenko, building on work by Spensky and Sipachova and others, which gives us a relatively concrete description of a neighborhood base for the neighborhoods of 0.
What is the discrete U sub x?
What's the question?
What is discrete U sub x?
So it's just for the university.
Just here.
Ah, okay. Yeah, all right.
It's the universal uniformity. In other words, for empirical text space, it's just the neighborhoods, neighborhoods around the diagonal in X squared, right? So you just take neighborhoods to the diagonal, right? You take pairs of elements from them, and you form these differences. You add them together, do this over a sequence of neighborhoods of the diagonal, and these are our basic elements. Okay, so this is a lot more concrete. It talks about things which deal with X, or at least X squared, so we have a relatively good idea of what's going on there. Okay, and what Nicholas and Karchenko did in a couple of papers, once they come up with this description, they were able to put it to good use, and they were able to show that in certain cases, they were able to calculate the character of the argument. In other words, the cofinality of the neighborhood filter, and it turned out to be D dominating. And they also showed that there exists at least one set of geometric space where the character is a continuum in ZF. Now, this little list here is more or less the start of the Borel hierarchy. It's the most basic elements of the hierarchy. So just to remind you, if we then move up through the hierarchy, we break into omega 1 levels. If we then take continuous images of the absolute Borel sets, we get analytics, complements, and co-analytics. And they asked, if we move beyond those first few levels, do we still have the character being equal to D? And the first theorem says yes. In fact, it says yes when we have X in analytics. So we can calculate the character in this case. On the other hand, when you take the complements, you go to the next one, consistently says co-analytic set, whose character is strictly bigger than D. So that answers the question. Won't spend too long on that, but in direction of diversity, again, they struggled to show that there are actually many different ones, but they did manage to show that we have the ones which are Polish, for example, and then there's this example of one where it's C, so at least consistently you manage to find two which are different. So the diversity results that we have are that there's actually a maximal family, so 2 to the C, by this number of acceptable metric spaces, whose free abelian topological groups are all different. And the thing I want to emphasize here is that in fact we have a rather stronger result, which is that if we take any two elements from the family, neither one embeds inside of the other topological groups. So they're not just different as topological groups, they're not even not homomorphic, they just don't like each other at all, right? They don't embed one another. Even less relevant to this talk is that there's also a game which you can get where they embed in a tower of length C+, which is the maximal possibility. Okay, which brings me on to the two key parts. This has been my obsession for the last few years. Basic setup is that the 2Q order allows us to compare directed sets. It tells when one is bigger than another. It doesn't really matter what the definition is. I'm not going to spend any time on this whatsoever. Just think of it as being a broad way of comparing directed sets. Right? And I can tell you the main theorem. So the main theorem is that we have a very good understanding of the structure of the neighborhood filter of 0 in the free abelian topological group, and up to this equivalence relation. This is the one. And again, this needs a few explanatory words. So curly K of a space-Y is a collection of compact subsets ordered by set inclusion. So that's good. N to the N we know. Then I have to explain the X check here. So the X check just means that whenever you have a space, separable metric space, take an arbitrary metric compactification. The check is the complement, it's the remainder. Okay. Now you're going to tell me there are lots of compactifications, and I'm going to say, sure, but I don't care. In this context, in terms of the compact subsets and working up to 2 equivalents, it's exactly the same thing. So it doesn't matter which remainder I take, it's always the same. X check. It's also useful to know that we can assume that the double check is just X itself. It does the same sort of thing. Okay, so there you go. So up to 2 equivalents, we have a good description of the order thing. And what this means is that instead of trying to understand this guy, I understand this guy. And this is what I've been working on, so I have some understanding of it. And so when we're talking about calculating cofinalities, it turns into thinking about the cofinality of compact subsets of a separable metric space. And the only thing is that things are dualized, right? So co-analytic and analytic, they get flip-flopped over. That's what the check does. And it just works. This is true. And it's just true that there exists an analytic set such that the cofinality of compact subsets is strictly larger than D. So taking the check and then the check again, we get exactly where we want to go. And the diversity, same process. So the idea is that instead of worrying about neighborhoods, I just think about the compact subsets. And again, because the double check gets us back where we started, I can think about starting with making the M check, and checking again. That's okay, everything works out. So what we do is to find this large family where the free Armenian topological groups are all different. We don't think about that, we think about these separable metric spaces, and we ensure that this guy does not produce quotient to this guy. And that's enough because it's pretty trivial that when you have a point in a subspace, in a bigger space, if I have a neighborhood in the big space, then I just trace it down onto a subspace. This obviously, surely, will give me a nice Tukey map. And so the neighborhood filter in the big space quotient subspace. And so that automatically says it's impossible for one of these AN to embed in AN because Tukey relation doesn't hold. So we'll get the non-embedding as well as the normalized orders. All right, so that was things I wanted to tell you, so I can get on to the new bits. So the new bits are situation where this Tukey approach doesn't work. Now, it works when we have interesting but slightly unusual separable metric space. If we have a compact metric space, it does not work. We know exactly what the Tukey equivalence of the neighborhood filter is. It's an n to the n. And they're all n's, so nothing is distinguished. So Mikolai, who's visiting, he's doing a postdoc in Pitt. He showed me this very nice construction using the support map of a continuum size family of curves. Curves are one-dimensional continuum, compact metric connected. And they have the property that, again, any two distinct elements of the family, the free topological group on the first one is not embed in the free topological group of the second. Why continuum? Well, there are only so many compact metric spaces, so this is optimal. But the curves that he uses are related to the Cook's curve, which if you know anything about it, the only thing you need to know about it is that it's weird. It's very strange indeed. Has lots of wonderful and very odd properties. So what we would like, since we're making families of spaces which do things, is that we would like to have much nicer continuum, for example. What about ones which are locally connected? Piano continuum. Okay, and that's where I'm going to get to. So before I get to it, let me point out that there's an extra roadblock here. So here, again, we have this strong non-equivalence. We have a non-embedding. That's not absolutely necessary for our problem. The only real thing we need is the first isomer on the list there, which is that they're not isomorphic. We could do other things, but we really need the first one. And going for this stronger version is not a good idea when we're looking at piano curves, because piano curves contain paths, those in the dimples, and it's a consequence of a result of Lehmann and Estoff and Morris, I think, that whenever you have your nice compact metric space and it contains an arc, then every single A of Z, where Z is finite dimensional compact and metric, embeds as a closed subgroup into your free Archimedean group. Right? So you can't distinguish it based on embedding. It's not going to happen. You have to go for something a bit different. And in fact, what we'll end up with is we'll show that and not pairwise homeomorphic. So we've still got a strong graph. And how do we do that? If I showed you all the things which I did here to make this work, you'd probably run me out of town. There was cohomology going on, other weird algebraic. I just wanted to get the answer. So I've managed to eliminate most of that. We'll probably still manage to talk. Let's see. Okay, so the idea here is that we're going to focus on looking at the continuous maps between spaces that we're interested in and abelian topological groups, and we're going to work up to homotopy. It turns out that if the free abelian groups are homomorphic, then these corresponding homotopy groups are isomorphic. Okay, no topology.
Here both X and I are compact metric.
Yeah, everything here is to do with compact metric space. Everything. We're going for nice things. So we're looking at continua, we're looking at one-dimensional continua, we're looking at piano things. They're nice. I mean, strangely nice, but they're nice. So these guys are actually homeomorphic. Isomorphic situation. And this is the invariant that we're going to use to distinguish these. And there's kind of a classic family of things that we can do here. So we're going to do some basic duality. Torsion-free rank 1 abelian groups are what you do when you have lots of reciprocals of primes. Turns out very easy to see that if the sets of primes are almost disjoint, then the corresponding groups are non-isomorphic. Okay, looks suspicious. Let's turn it into a little bit more topological. We can take the dual group. And now this turns it from a discrete countable abelian group into a compact metric group. Because these guys are rank 1, these guys are one-dimensional, because these guys are torsion-free, these guys are connected. In fact, they're solenoids. You know what a solenoid is? It's when you zoom the torus around on itself. You can choose how many times you go around at any particular level, and that corresponds to the set of primes. And these are good because they're both one-dimensional, they're curves, and they are abelian topological groups. So they manage to do two good things at once. And the easy way to get a nicer family is to do the following. So we can take our almost disjoint family of sets of prime numbers, and we think of it, first of all, as the space, and then think of it as being an abelian topological group, and we look at the functions between them. And I can think of at least one which works when it's the same domain and target, namely the identity map. But it's also true based on properties of solenoid. There are absolutely no maps other than constant maps, which are when the sets are different. So that tells you immediately that this family of solenoids is a continuum-sized family of spaces whose free abelian groups are all going to be different. Okay, solenoids are not locally connected, however. But there's a trick. There's this funny trick you can do. It's like an advert on the web, isn't it? It's a funny trick you can do. And you can pianify basically anything, any compact metric space, you can make it into a piano thing, because every compact metric space is an image of the Cantor set, and then you just glue in kind of arcs and edges by filling in the gaps in the Cantor set. So you pianify it, and that gives you a one-dimensional curve in our case, and that's what you do. This is the family of spaces you take, pianification of those solenoids, and then you have to do some work. We're now going to map into the circle group over here, and because you've added all of these different arcs, there's a lot going on, but we show that these two groups are non-isomorphic, pairwise, and therefore these spaces here are our piano continuum, which have non-homeomorphic. Right, and a couple of minutes early. Finished.
Are there any questions from our speaker?
Yeah, one question.
Yeah.
Do you have any result for non-abelian?
Well, if the non-abelians are isomorphic, then the abelians are isomorphic.
I don't know here, but you speaking about...
Okay, yes. I mean, it is true that if the non-abelian free topological groups are isomorphic, then... homeomorphic, yes. That's a good question. Okay, I don't know based on homeomorphism. Yeah, I'm pretty sure I could do much the same kind of thing though. Actually, I can still do the same thing, can't I? Because I can still look at these guys here and there'll still be invariants. Yeah.
This is a naive question, but you know the fundamental group can be non-abelian. So why are the homotopy classes for an abelian group?
Because it's coordinate-wise. These are dual. So actually, these homotopic groups, they're like cohomology. They're the dual things. They're cohomology. But the answer is that. This is basically C of x, G. G is abelian, so we're doing things coordinate-wise. So it's already abelian, and then we're taking homotopy classes. That's the answer to your question.
I wanted to ask you about the theory. It's quite interesting, I think. I did not catch the theory if A of X and A of Y are only one thing, then this.
Okay. So if you look in the book by Arhangelski and Karchenko, you'll see this for the free abelian group. So I just stole it. So I just put in abelian group.
Yes. So this result is in the book.
Oh yes. Yeah.
Thanks. How complicated is the proof?
Not very, I don't think. No.
Thanks.
At the end of the book.
Okay. Oh, I didn't got it.
There's too much in the book.
I like it. It's a good book.
Do you know what happens if you go down farther where there's no loops at all? Like if you just have a piano continuum with no, like if you have a closed interval versus like a triout or something?
Great question. Okay.
It seems like this is something totally different.
Right. So actually, classically, I think it's Gruenhage who was looking at these, managed to show that the circle and the triad had different free abelian topological groups. And yes, I would like to know, and I would really like to know for types of spaces which I call graph-like, so they're kind of like infinite graphs and things. I would really like to know if we have to distinguish them, but it turns out it seems quite hard at the moment. A lot of my work has been on these graph-like spaces recently, and so I'd love to know that, but I don't.
Any other questions for our speaker? Let's take hold again. So we have 5 seconds to lunch. For about 20 years as a teacher, as an advisor, a mentor, and a friend. And I'd just like to pile on that you have been such a positive experience in my life. So one of the things